And our first speaker is Dr. Alan Blaylock. He's a senior agronomist with Nutrien. Alan holds a master's degree from Brigham Young University and a PhD from Iowa State University. Having managed both domestic and global research and educational programs, Dr. Blaylock has a wealth of experience in applying science-based nutrient management principles and practices to solving practical questions. So with that, Alan, take it away.
I have a colleague with another company, a close friend of mine, so we were in graduate school together. When he gets up in front of an audience like this, he literally is yelling. People in the next room complain that he's so loud. Really energetic, so I'll try not to do that. We're going to talk about some topics that I've been working with for most of my professional career, this world of enhanced efficiency fertilizers, and then we'll have some comments about some other emerging technologies that may interest some of you. So with that, let's get into this. And, you know, we just had the big football game, right? That thing called the Super Bowl. And I've used this analogy in a number of talks, but when we're dealing with nutrient management, we have kind of a playbook. That's our suite of practices that we implement. And so think about that as a football analogy. What constitutes a successful plan? What is a win? How do you win in nutrient management? Is it profit? Is it costs? Is it yield? Is it efficiency, or some combination of these, some measure? How do you judge a win? And what are the plays that are going to get you there? And do you adjust that playbook maybe as the season goes on or from year to year? Are you monitoring how those plays perform? How do certain practices perform for you as things change? And so I'm going to give you the take-home message, and if you get nothing out of this talk except this line, this sentence, please remember this message, because this is a message that is really in our nutrient management world, and especially dealing with enhanced efficiency fertilizers. There is a lot of misunderstanding, and we'll get into a little bit of that. We have to match the product, its mode of action, with the problem we're trying to solve. If we don't do that, we spend money on technology that does not provide a benefit. So this is absolutely critical. And so while we could go into a very lengthy discussion of all the technologies and all the different problems and all of that, I want to stay at a little bit higher level, because there are lots of other resources. And I know Fabian has talked about this topic many times. Jeff Vetch over here on the other side has talked about these topics a lot of times. So there's lots of sources for all the details, the nitty gritty. And it would be about a 3 or 4 hour talk if we got into all of that. And I don't want to take that much of your time. I'm not allowed to take that much of your time. So I want to stay at a little bit higher level and talk a little bit more philosophically about this idea of matching our playbook with the goals, the problems we're trying to solve. Okay, so you all know about the 4 R's, and so we're going to talk about these products as components of a 4R system and how they fit into that. We're going to review just briefly nitrogen losses. We're not going to go into a big dissertation of the nitrogen cycle. As I've said, you can read about that in many other places. We'll give you an overview of the different products, because there are some major categories of products. There are lots of actual products within those categories, but we'll look at the categories of products. We'll talk about their modes of action a little bit. And then I'll give you just a few examples of performance. And particularly, I pulled out examples that particularly relate to this concept of matching mode of action to the problem we're trying to solve. So we're not going to get into a big data dump. There's lots and lots of data on these products out there. Some of these products have been in the marketplace for half a century. So most of these are not new. There may be some new formulations or new brands, but most of at least the major products are not new to us. We know them really well, and we know how they work really well. So you can find this information and get into those details. All right, so I would submit to all of you that maybe we need to rethink how we manage nitrogen, because this is a changing world. There are lots of things that are changing. including the climate. And that climate change means changing weather patterns. And there are some significant things that affect how these products might be used or their benefits. One of those is, and this is well documented for Minnesota, increasing rainfall, but not just increasing rainfall, increasing percentage of that rainfall occurring in large rainfall events. The big storms that really are the main drivers of nitrogen loss. Those slow, steady rains, they're not the big drivers. I think Fabian has said that most of the nitrogen loss in Minnesota occurs in 4 or 5 major rainfall events each year. So these are the events that we're concerned about, and those events are becoming more common. More of our rainfall is occurring in those big events. So these changing weather patterns change the value of these products and may make them more valuable in certain circumstances. Food companies are starting to ask growers to grow their crops in a certain way and starting to specify, you want to sell to me, you will grow the crop the way I tell you to. And so they're starting to specify these practices. There have been lawsuits like the one, Des Moines Waterworks versus the farmers in north central Iowa, suing farmers over groundwater contamination or contamination of the Des Moines River, Raccoon River, I guess it was. But so this litigation is occurring, and we have nutrient loss reduction strategies, fertilizer management rules. One of the most profound to me is one in California where they're growing these vegetable crops, high value crops that often need a lot of nitrogen and they have shallow roots. And they have a new law as of a few years ago that requires water passing beyond the root zone to meet drinking water standards with regard to nitrates. So how do you do that and grow a crop like lettuce that is so shallow rooted and needs a lot of nitrogen at certain times? So some of these things present some real significant challenges. So I suggest that we need to think maybe differently about how we manage nitrogen. All right, so as I look at nitrogen loss, I divide it into kind of 2 broad types of losses. One is this loss called volatilization that occurs when we apply urea on the surface or misapplication of anhydrous ammonia. If we don't get that slot sealed, we can lose some of that. And this is a short-term loss. This loss occurs really within a few days after application. So in this case, we're managing loss for the short term, for kind of an immediate effect of that fertilizer application. And so we have to think about what happens right after application, within a few days, and how we might be able to treat that. The other losses are losses that occur from the nitrate form of nitrogen. And there are 2 types of losses that are important. One is we call leaching, which is the downward movement of nitrogen beyond the root zone. That gets into ground and surface waters. And the other is denitrification, which is a gaseous loss when the soil becomes anaerobic, saturated or nearly so, and organisms take the oxygen off that nitrate and convert the nitrogen back to one of various gas forms, including nitrous oxide. So both of these losses can occur anytime during a season when we have nitrate present and we have excess water. So this is those big rainfall events that contribute to losses. The leaching event, if we have a soil that's permeable and the water can move through it fairly readily, or in our heavier soils where the water can't move through and we deplete the oxygen. So anytime we have nitrate present and we have excess water, these losses can occur. So these losses we need to manage for the entire growing season, really. Now, I say the entire growing season, but we need to put a caveat around that. And that is when the crop is growing very rapidly, particularly with corn. Corn is a very aggressive nitrogen feeder in its rapid growth phase. And so but it's also taking up a lot of water. So that period of time during that rapid growth phase and into the early grain field is a period of time where even though we may have these events and we may have nitrate present, there's less susceptibility to loss because corn is trying to get everything it can during that period of time. So the critical time really to manage this is really more in the early part of the season. We're typically wetter. We don't have a crop taking up a lot of water and nitrogen. So that's more of a critical time. Now, it doesn't mean the losses can't occur later. And I'll give you an example in our data when we get into those examples. I'll show you an example of that specific type of thing. But nonetheless, we have short-term losses and we have season-long losses, and we want to manage accordingly. And different products would be used for these different types of losses. You don't use the same thing for ammonia volatilization that you use for leaching control. So again, keeping track of that message that we have to match mode of action with the loss mechanism. All right, so what are our options to reduce that loss? And why do we want to do that? Well, obviously, any loss is an economic loss. Every pound of nitrogen that leaves the field is a pound of nitrogen for which the farmer spent money and he gets no return, no benefit. But we also have environmental impacts from that nitrogen that leaves the field, either air quality or water quality or both. So whether environmental quality is a driver of your decisions, and it probably should be, it's also, those two, the economics and the environment are tied together because that pound of nitrogen you had to pay for in some form. So there are different approaches we can use. We can go to our 4R principles, and there are lots of practices, and throughout the day you're going to hear about a lot of these practices for different forms of nitrogen, different things you can do to reduce that risk of loss. And this really is about risk management, because I don't believe we can completely eliminate this loss. The soil is a leaky system, especially with regard to nitrate and other forms of nitrogen. It's leaky. Nitrogen is very transient in the soil, and it converts readily from one form to another, and this leads us to that risk of loss. So I don't think we can eliminate it completely, but we can do a lot towards reducing that loss. So split applications, for example, applying the nitrogen closer to the time of peak crop demand, because that's a time of lower risk than when there isn't a crop growing. Put nitrogen on in the fall, we have many months of risk of that nitrogen doing something we don't want it to do. Or we can, for example, with urea, we can incorporate it, get it into the soil quickly so that we reduce that volatilization risk. We get it incorporated a couple inches, it's not going anywhere. The soil, in most cases, will trap that ammonia and it won't be lost. So these are some examples of the types of 4R practices that we would implement depending on our source, depending on the time of application, depending on our loss mechanisms that we may have. Now, we can also modify the fertilizer. Now, I put and or here because I would hope that we're combining our technologies, our products, with these other 4R practices. But altering the fertilizer may allow us to change the timing, for example. And I've listed a couple examples here. For example, we can use a slower control release product to use fertilizer technology to deliver the nitrogen closer to the time of crop demand. So we may be able to substitute a product technology for a timing, a mechanical operation. Or we may be able to use a nitrification inhibitor to slow the conversion to nitrate, which also gives us some time. Because if it's in the ammonium form, in most soils, that ammonium won't be susceptible to leaching. It's more stable. And so if we can hold it in the ammonium form a little bit longer, we can reduce the risk of that nitrate loss. So these are, again, some examples of how a product choice might modify what we do with our other practices. And if we can combine these things together, we can get the best of both. That's our goal, really. So the definition of an enhanced efficiency fertilizer, the official definition, includes two components. It's a fertilizer that's been modified in some way to, one, reduce nutrient loss, and two, increase nutrient availability to the crop. So under the APFCO definitions, the language, these are the two components of that definition. So both of those really go hand in hand. And there are a variety of benefits to these products depending on when and how they're used. It may be to reduce phosphorus or reduce nutrient loss. Now, most of these concepts really apply to nitrogen, but there are some enhanced efficiency phosphorus materials and sulfur and some of the other things. And we're going to focus on nitrogen. Ultimately, we want to improve nitrogen use efficiency. And that concept can be defined in different ways, but basically it's conceptually, it's getting more output for each unit of input. And there's different ways it's calculated, but that's the basic concept. We want to get more for the input. We can use some of these materials to regulate the timing and form of nitrogen supply to the crop, like the slow release fertilizer. It regulates when that nitrogen becomes available. In some cases, we can use it to simplify some of our other practices, like the examples we've already given. In some cases, this is particularly popular in Western Canada, where in the dryland wheat and canola systems, they really like to apply the fertilizer with the seed in the seed row. All these direct seed, one pass, no-till systems, where they're doing everything in one operation, and they like to put the fertilizer with the seed where possible. There's some good reasons for that. One is you drop off the extra openers that might be used to ban fertilizer that open up the soil and cause moisture loss and require more horsepower. So putting the fertilizer with the seed, if we can, has some advantages. So you would have to have a safer fertilizer than our conventional materials in order to put more of that with the seed. So that could be a potential benefit, but ultimately it's this idea of increased productivity and profitability, which go hand in hand with environmental safety. Okay, so two broad product categories that we'll talk about. One is the slow and control release fertilizers. There are different forms of these materials, and they've been used in, excuse me, turf and horticulture for many decades. The first coated fertilizer, polymer coated fertilizer, was introduced in the US in the late 60s. So it's been around a long time, but largely been confined to turf and horticulture applications because of cost. But more recently, more of these products are being introduced into agriculture, like some of you will have heard of our ESN product, Nutrien's product, which has been in the market for close to 25 years now. So this is an alteration to the fertilizer that reduces the loss by slowing the availability of the nutrient, by metering that fertilizer out over a period of time, hence the term slow release. The other broad category is what we call inhibitors or stabilizers, and these are chemical additives that are added to the fertilizer to change the behavior of the nutrient in the soil, change the alterations, the transformations of nitrogen in the soil, to alter some of these microbial processes, to keep the fertilizer in one form or another based on the loss we're trying to prevent. So reducing the amount of the susceptible forms in the soil, like nitrate. So we're going to break these down just a little bit further now. All right, so we have these inhibitors and stabilizers. These are chemicals that are added to the fertilizers to slow the reactions. On one hand, we have what we call urease inhibitors. Urease is the enzyme that converts urea to ammonium in the soil. And urease is everywhere. It's all over in nature. And so that enzyme is not limiting. So urea conversion to ammonium, which we call hydrolysis, goes very quickly within 2 or 3 days. So we can use the chemistry to block that enzyme or slow that reaction down for typically about 7 to 14 days. And that depends somewhat on the conditions, somewhat on the application rate of the product and the specific formulation, but typically about 7 to 14 days. So what value do we get from that? Well, since most of the volatilization occurs within the first couple of days, we can spread that conversion out a little bit. We reduce the concentration in that reaction, and we reduce the volatilization. And so for 7 to 14 days, that gives us more time to get a mechanical incorporation, to get rainfall on it, or irrigation to push it into the soil. But even without those other things, it does reduce the volatilization because it's slowing that transformation down, and it's the high concentration of ammonia that's being involved in that reaction when it happens very quickly that drives the ammonia off. So we don't want to stop that process because the plant doesn't take up urea. It needs to take up ammonium or nitrate. So we don't want to stop it. We just want to slow it down a bit because that's how we reduce the loss. Some of the products in this group are, the one that's probably best known is Agritane. It's a product formerly sold by Coke. They've introduced a new formulation. Nitrien or Nitrien Express, which is an Agritane type product, same active ingredient. The active ingredient is called NBPT. Don't ask me to say the chemical name. You know, eventually I'd get there, but N-butyl phosphorylamide or something like that. Anyway, I probably butchered that, but anyway, there's a product from BASF called Lemus, and that is a combination of NBPT with another compound that's very similar. So again, it's in the same family, and lots of other brands. So because NBPT is a generic compound, it's available around the world. There are lots and lots of brands, and many people have their own proprietary versions. One of the critical things to evaluate is the concentration of the active ingredient in the actual product. So you want to pay attention to that. All right. Polk has introduced a new chemistry called Duramide, sold under the brand name Anvol. So some of you probably have seen that product on the market. And then our thiosulfates have also been shown to have some inhibitory action, maybe not quite as good as NBPT, but if you're mixing liquids, it may be an option to, say, put ATS with your UAN and get some benefit, some inhibitory benefit off of that. On the other side of the equation are the nitrification inhibitors, and they slow the conversion of the ammonium to nitrate. So put urea in the ground, the first thing that happens is it converts to ammonium, and then the next thing is the ammonium converts to nitrate. And this leads to that long-term loss potential, that season-long loss potential that we talked about. And these control leaching and denitrification, typically in the range of 4 to 8 weeks. Now, depending on the conditions and the product, like if you put nitropyrin with ammonia in the fall, you get a lot more than 4 to 8 weeks control. Because the soil is cold, the bacteria are slowing down, becoming inactive. The ammonia itself is toxic to those bacteria, so it puts a hit on them, and you couple that with the nitropyrin, and so you really get longer protection in this 4 to 8 weeks. So the reference for this would be, say, if I'm making a spring application with one of these products, this 4 to 8 weeks would be from that time, typically. So there's obviously caveats to all of these, just putting them in general terms. So some of the key chemistries that we have are nitropyrin, which was introduced in, I think, 1972, if I'm not mistaken. Been around a long time. We know it well. And that's sold under the brand Enserve or Instinct. In Canada, they call it Entrench. Another compound that's been around even longer is a compound called DCD. Was it discovered in the early 20th century, late 19th century? It was thought at first it might be a slow-release nitrogen form. It's a nitrogen-rich compound, but then it was discovered that it was inhibitory to this nitrification process, so it blocks that enzyme. There are some concentrates that you can purchase with the DCD. One of the biggest challenges with this material is it takes a fairly high volume of this concentrate on something like urea, and so to get a high enough rate of the active ingredient, you kind of get a sloppy mess, and so you need to use product drying agents, things like that. But it is a very effective compound. Koch has also recently introduced a new chemistry here called pronitridine, sold under the brand Centuro, that seems to be very effective. It's only been out for a couple of years, so we're still seeing data coming in on that, but it seems to perform pretty well. And again, the thiosulfates fall into this category because the thiosulfates seem to have some inhibitory action, and Jay Goose at North Dakota State studied thiosulfates pretty extensively and documented a lot of this benefit. Then there are some products kind of here in the middle that are a combination of the two inhibitors. So products like Super U that use both the NBPT and the DCD, put them together in the urea, so you get both actions, and some other brands that do the same thing. And then there are some other active ingredients that are not as well studied, or the mode of action is less well understood, or the benefits not as well documented. So some other products under some other brands. So in any event, if you're uncertain about how well the product fits, do a strip trial on farm. Test it under your own conditions and see how well it works. Okay. You have to wave your hand on time, Fabian, keep track of me because I'll keep going. Then we have these fertilizers that release nitrogen over a period of time, the slow and control release fertilizers. And there are a couple of different major mechanisms. One is those materials that release nitrogen by a physical process. These tend to, and those then that release nitrogen by a chemical or biochemical reaction. So these products generally control nitrogen loss for a longer period of time. Now, this can be very product specific. in the world of these coated fertilizers, which is the group on the left, there are products that may last as long as a year, used in some of the turf and horticulture applications, like growing container plants in a nursery, and you want to be able to load that pot up with nutrients without killing the plant. And so they might use some really long-lasting products growing under hot conditions in a greenhouse, and you really want to protect the nutrients. So, but in agriculture, the main brand you would see is our ESN product. Polyon has had some presence over the years, never made a big impact because it was a little bit expensive, but was used in some ag applications. Duration, a new product on the market from a startup in Alabama called Purcell Agritech, Percoat. I don't know if any of those products are making it into this part of the world. They are being sold in the Southeast and some in Eastern Canada. But these are all similar technology. It's a polymer coating, put it around the fertilizer. It acts as a semi-permeable membrane, allows water to move in through the coating, dissolves the urea inside, and then that urea diffuses out over time. So it's a physical release mechanism. The coating stays intact, but it's a physical process of that nitrogen being released. On the other side, we have biological processes. These are complex molecules that have to be microbially degraded to release the nitrogen. So things like methylene urea, urea formaldehyde, urea triazones. Interestingly, some of these products are used not really for their slow release properties, but they're used as foliar treatments. And they don't really behave as slow release in a foliar treatment because the leaf absorbs them very readily. They're kind of favored for foliar because they have low phytotoxicity and they're pretty effective. They're metabolized very readily. And so they work very well for that application, but that's not really a slow release application. But when applied to soil, they do have to undergo these reactions. The challenge is they're a bit expensive per unit of nitrogen to apply any significant amount to the soil, but it could be used that way. And there are products in this category that are used in golf courses, for example, because you can grind them up really fine into powders without destroying their slow release property. You take a coated product and grind it up, it's not slow release anymore, it's just urea. So you can grind these up really fine and put them on a golf green and have slow release fertilizer without interfering with the putting play. So there are some interesting properties there. And then we have something called sulfur-coated urea. It's kind of a hybrid between these two mechanisms. We coat it with sulfur, so it's a physical barrier, but the mechanism of release is more biological. That sulfur coating has to be broken down. So in contrast to the polymer products where the coating stays intact, the sulfur coating has to fracture in some way. And it's elemental sulfur, so it's subject to biological oxidation, and the microbes go to work on that coating. And once there's even a little pinhole, then the urea can come out. All right, so let's look at a few data examples. This first one is an example I got from a colleague of mine, Greg Schwab, used to work for Coke, and he provided me with this data. And this is a really good example of how to match up products with loss mechanisms. So we have 3 years of results here. The first year, so we have untreated UAN, UAN with Agritane, and UAN with Agritane Plus. So Agritane Plus is the dual inhibitor. So the first year, we get a nice bump in yield from the Agritane alone, from the urease inhibitor, and we get an equal bump from the nitrification inhibitor. So what does that tell us about the loss mechanisms that were probably occurring? We probably had both kinds of losses, both volatilization and leaching or denitrification in this case, because we got a response to both products. Okay, then the next year, we get a nice bump in yield from the urease inhibitor, but we don't really get anything significant from the nitrification inhibitor. So loss in that year appears to be really dominated by volatilization and not much of the other. The third year, it's the reverse. We don't get a benefit from the urease inhibitor, but we get a nice benefit from the nitrification inhibitor component, the Agritane Plus. So how do you decide which of these products you want to use? Well, most of us, I think, know a little bit about our soils. We know about our weather conditions. Now, we can't predict the weather, but we kind of know what to expect in Minnesota. We know we're going to have wet periods, and we're going to have these rainfall events in the summer. So you can look at long-term patterns and draw some inferences and look at the type of soil you have. If you have a sandy soil, you're more likely to have leaching. If you have a heavier soil, more likely to have denitrification. So you can look at those things. But when we average this over the 3 studies, we kind of, or the 3 years, we kind of mask some of those differences. So it's important in looking at the data to look at individual conditions and say, where did this product really work? Because if we just average it together, it would say, oh, you use the Agritain Plus all the time, but maybe you don't need to use that all the time. You have to look at your own conditions. So this is a great example of that concept. Now I've got another example here. This is out of University of Nebraska. It's irrigated corn. And I'll start by showing you the rainfall data. We have 3 years of very different rainfall distribution. The first year, it's pretty dry early, as you can see. And then we get some rain later in the season. The second year, it's really wet early. And then we get some more rain later. And the total is near normal. But the third year, we get a lot of rain early, and then we also have more rain later on. So this is going to affect the results. Now I'm going to show you 3 graphs for the 3 years, and they're going to look like this. We have the check, which is the, see if I can do it this way so everybody online can see. We have the check, which is this red square. That's the recommended University of Nebraska split application. So I think it's 40% pre-plant, 60% side dress. That works really well because it avoids much of that early season loss. We're applying most of the fertilizer later on, but there was some loss there because the pre-plant UAN didn't do very well. So there was some kind of loss working on that. And then we have the ESN, the control release, that's all applied at planting, and that's performing similar to the split application. So again, that technology can substitute there. The next year, he added some inhibitor treatments. We see a similar pattern. The split application does well. The ESN does well, performs similar to split application. The inhibitors have some benefit, maybe not as good as the split application or the control release. And there's a reason for that. This is sandy soil, low cation exchange, and the benefit of retaining the ammonium form is not as great because we don't have the cation exchange capacity to hold the ammonium against leaching. Okay. So then the third year, what happens to the split application? Well, because there was more rain later in the season, so the first month is fairly low rainfall total, but the remainder of the season, we had a lot of rain. And so even the side dress application was exposed to those leaching losses later in the season, these rainfall events that we talked about earlier. And the interesting thing here is that the pre-plant UAN and the inhibitors really didn't produce a significant yield increase. If you, when I ran the economic calculations on this, on these lines here, you'd be better off economically to apply no fertilizer because the cost of the fertilizer was not recovered in any increase in yield. But in this case, the control release produced a similar response to the previous 2 years because it's protecting for a longer period of time. And the cation exchange is not entering into that part of the loss equation. So again, illustrating the importance of how these things come together. All right, I'm going to jump to a couple of things, and I'm not going to get to some of the other things I wanted to talk about because I always talk too much. This is a summary of a bunch of different studies and the environmental benefit of some of these products. And so you can look down here and look at the percentage reductions in some of these various losses. And so those are really meaningful reductions. If you can reduce leaching or denitrification loss by 80% or 50% or 30%, that's a big savings with a pretty big environmental impact. There are lots of these, what we call meta-analyses have been done on these products, and there's lots of information published documenting these environmental benefits. Even from Fabian here in Minnesota, and I just went past his data. So, but I want to hit this slide before we close. These are some reactions that I hear in the marketplace from different people, customers, farmers. Oh, they're all the same. I'll just use whatever's the cheapest. Well, what are you trying to achieve? Does that get you there? You just use the cheapest product. Are you going to get the value, or are you throwing your money away? If you're just going to the cheapest product, what do you get? The cheapest product. The other one is, I tried that and it didn't work. Well, How did you try it? How did you use it? What were the conditions? Was it the right product for those conditions? So again, thinking about that, but these are reactions that people have told me, and this last one really bothers me. And this was a comment that was made after a fairly long conversation about in-loss and products, and you know, we went round and round about mechanisms of loss that were at play and how they were doing things. And the guy eventually said, well, you know, in the end, it really doesn't matter if I use the right product. I just need to be able to say that I'm using an enhanced efficiency fertilizer. Now, what does that get us? That's really missing the whole point of our nutrient stewardship and our 4Rs and the point of the technologies. It just gives a bad name to all the technologies to take that kind of position. We want to be matching modes of action with the problems. And so I'm skipping past all the other good stuff we could talk about. It'll be an hour-long talk in itself, the way I'm going. Anyway, thanks for the opportunity to be here. There's lots of good stuff you can find to read on these products that, so get informed, know what your loss mechanisms are, understand your soils, the processes. There's lots of experts in the room that can help you with that, lots of resources, and then understand the products. And there are same resources here, and I'm happy to help anybody with that. If they want to contact me, it's somewhere here. I think I've got the contact. So with that, I better stop.
Thank you, Alan. So keep it on for a moment for Q&A.
Okay.
All right, so now is the time for questions. And so again, as a reminder, use the Slido, type your question, vote them up or down, depending on your interest. And we'll get started.
Questions, answers, dumb looks?
Live questions from the room.
Yeah, so let's do the live questions from the group here if anybody has a question. But again, as you listen to the presentation, I would encourage you to be typing those questions. They will be just accumulating during the presentation, and then when the presentation is over, we can start going through those questions. So, but for now, are there any questions here from the group that would like to be asked in person?
Looks like I should have planted some questions. Yes, Bruce.
Program or Nutrien ever consider putting different thicknesses of ESN on to more localized products used for climate conditions?
Yeah, so the question is, have we ever considered using different coating thicknesses to get more, I'll say, specific products for different purposes, different geographies? Now, that is an interesting question. We formerly owned a business that had lots of products with different release rates, and those one of the things that does is drives up cost. And so, yes, in the horticulture and turf world, there are products with all kinds of release rates, from as short as 40 days out to over 300 days. So, yes, we've considered that, but we have two large production facilities that are not really well suited to changing that all the time. And so that creates complications that would drive up cost. And so in the interest of broadacre agriculture, cost is really important to make it economically viable so that it's a technology that growers can actually use. And so, yes, we've considered that, looked at that. We know how to do it. It is possible. Other product lines do have those options. We have not done it in Nutrien in the present.
Next question is, could you briefly explain how ATS works for inhibitions?
No, I do not know the exact mechanism there and how that works. I could look that up and find that. I suspect it's something in the thiosulfate itself, in that transformation, or in some specific toxicity of the thiosulfate, or something. It's something to do with those enzymes, but I do not know the exact mechanism there. But I certainly should look that up, I guess, and know the answer to that.
All right, next question. You share meta-analysis on the N2O reduction using these EFF products, the enhanced efficiency fertilizer products. Is there data on nitrate leaching reductions?
Yes, there is data on nitrate leaching reductions, and Fabian, Dr. Fernandez here, has collected some of that data here in Minnesota. So, you know, for locally specific conditions, yes, and they do, these products do generally reduce leaching if they're used at the right time, the right product, all of that. you can get those reductions, some case very large reductions. I think percentage-wise in your study is probably on the order of 40%, something like that. So yes, we can reduce leaching and the data is there. And in some of these other meta-analyses that I mentioned, there's data on that in those as well. So the answer is yes.
Is ESN considered a forever chemical?
ESN is not considered a forever chemical. The coating itself is a polyurethane material that's not on that list of the PFAS or forever chemicals. So no, it's not.
Good. And we'll do one more question. We are out of time. Do polymer-coated products contribute to microplastic accumulation in soils or crops?
This is a really good question. It's getting asked a lot these days. The answer is there's a lot of uncertainty about the fate of these coatings in the soil. It is being studied. The exact longevity of these polymer coatings is not really known in soil. Now, the EU has established a certain test method and a certain standard, and the EU requires that the coating break down completely, like 98%, within 4 years of application. And none of the polymer products currently on the market globally meet that criteria. So they're not, starting in 2026, they would not be allowed for use in the EU. Do they contribute to microplastics in the soil? That's a bit of an unknown because we don't know the overall longevity. Do they decompose in 10 years, 5 years? They don't meet the EU criteria by their method, but there was a study recently done in Canada that seemed to indicate that that coating degrades actually a lot quicker than some of our previous data. So there's a fair bit of uncertainty around the answer to that question.
All right. Well, thank you so much. And Alan's email is in the presentation, I believe. So if you have burning questions, you can definitely contact him. He will be able to answer those questions. Let's give him a hand. Thank you, Alan.